Okay, let's dive into this. Welcome to today's Explainer, where we're going to totally decode the secret language of physical science. Grade 8 science is all about observing the physical world around us, right? But it's also about understanding what's actually happening beneath the surface, all the way down to the microscopic atoms. So today, we're going to look at the defensible evidence of chemical reactions, and we'll learn exactly how to write them out mathematically.
Here is our macro to micro roadmap for today. We're going to cover physical versus chemical changes, the evidence of chemical reactions, interpreting symbolic equations, balancing the atoms, and finally, a quick recap and a transfer challenge.
All right, Section 1, Physical versus Chemical Changes.
So before we even think about writing equations, we have to separate what we observe from how matter actually behaves. And this brilliantly illustrates the difference. Macroscopic observations are the things we can literally see, smell, or feel happening. Think of the distinctly sweet smell in those brown spots on an overripe banana sitting on your kitchen counter, or a liquid visibly bubbling in a beaker. Microscopic interpretation, on the other hand, is what the atoms are invisibly doing, breaking apart and forming entirely new chemical bonds. Basically, the macro is what we sense, and the micro is what's fundamentally happening behind the scenes. Now, a physical change simply means the state or properties of the matter change, but, and this is key, its chemical composition remains exactly the same. Imagine a solid piece of wax melting into a liquid puddle. It looks different, sure, but it's still just wax. A chemical change, however, produces one or more types of matter that completely differ from the original substance. A classic example here is iron rusting. That orange, flaky rust is a totally different kind of matter than the hard iron, oxygen, and water that were there just moments before. Okay, time for a quick pause check. Is a boiling pot of water undergoing a physical or a chemical change? Think about it for a second. Well, the answer is, it's a physical change. Why? Because that liquid water is simply turning into water vapor. The vapor is still H2O. It's literally the exact same substance, just changing physical states from a liquid to a gas. Moving on to Section 2, Evidence of Chemical Reactions. It is time to put on our detective hats. We're looking for defensible macroscopic clues that indicate a microscopic chemical change is actually happening. You want to look for unexpected color changes, like that overripe banana we mentioned. Watch for gas production, such as the toxic brown nitrogen dioxide that violently bubbles up when copper reacts with nitric acid. And of course, keep an eye out for flammability and combustion, like the sudden burst of energy from a burning match or the slow, creeping formation of rust on iron. When you see these events, your chemical detective alarm bell should be ringing loud and clear. So the absolutely crucial point here is this. The defensible evidence we observe macroscopically confirms our chemical interpretation. Actually seeing these clues, the color changes, the gas, the fire, the rust, that's our tangible proof that atoms are rearranging invisibly to form brand new substances. Let's jump into Section 3, Interpreting the Symbolic Equation. Now that we know how to spot a chemical reaction out in the real world, how do chemists actually codify this into a readable symbolic language? Let's take a very specific reaction, the combustion of methane. In plain English, we read it like this. One methane molecule and two oxygen molecules react to yield one carbon dioxide molecule and two water molecules. This sentence translates our everyday words right into the core chemical concepts of what we start with and what is subsequently created. Translating that into symbolic language gives us a beautifully clear equation. We always start with our reactants on the left, CH4 plus 2O2. These are the substances we have at the very beginning. That arrow in the middle, that simply means yields or produces, and it points directly to our products on the right, CO2 plus 2H2O, which are our completely newly formed substances, reactants to start, an arrow for the action, and products at the finish line. To really master this language, we need to clearly define two very important terms, subscripts and coefficients. A subscript is the small number, like the little 4 in CH4. This defines the simplest whole number ratio of atoms. It literally determines the substance's identity. If you change a subscript, you completely change what the substance is. A coefficient, on the other hand, is the large number to the left of the formula. This simply tells us the relative quantities of the substances. Basically, it just tells us how much of it we happen to have. Now, what's really interesting about this is how that large coefficient 2 works. It multiplies everything in the entire molecule that follows it. So a 2 in front of H2O doesn't just mean 2 extra hydrogens. It means 2 complete, distinct water molecules. That gives you a grand total of 4 hydrogen atoms and 2 oxygen atoms. All right, it's time for pause check number 2. When balancing an equation, can we change a subscript to make the atoms equal? The answer is an absolute, definitive no. Remember, changing a subscript alters the actual identity of the substance. If you change H2O to H2O2, you literally turn refreshing drinking water into hydrogen peroxide, a completely different, undrinkable chemical. So we can only ever change the coefficients.
Section 4. Balancing the atoms. To mathematically prove our chemical detective work, we have to rely on a massive rule, the law of conservation of matter. It states that there is no detectable change in the total quantity of matter present when matter converts from one type to another. Put simply, atoms cannot be created or destroyed. What goes into a reaction absolutely must come out. Therefore, an equation must have strictly equal numbers of every single atom on both sides. Let's move on and see how this builds a perfectly balanced ledger for our methane combustion by counting atoms on both sides. Carbon, we've got 1 going in, 1 coming out. Balanced. Hydrogen, 4 in from our methane, and, thanks to our coefficient of 2, 4 out in the water. Balanced. Oxygen, 4 on the reactant side, and 2 plus 2 on the product side. Everything is perfectly conserved. Whenever you balance an equation by inspection, just follow this logical flow. First, write down the unbalanced equation. Next, count the number of each type of atom on both sides. Then, change only the coefficients to balance things out. And remember, never touch the subscripts. Finally, verify your sums to ensure total conservation of matter. If you stick to these steps, you literally can't go wrong.
And finally, Section 5, Recap and Transfer Challenge. We are at the final segment of our journey. Here are your energetic takeaways from today's explainer. First, macroscopic observations give us defensible evidence of reactions. Second, our microscopic interpretation tells us that atoms are physically rearranging themselves. Third, we use chemical equations to symbolically represent this exact rearrangement. And finally, we adjust coefficients, never subscripts, to perfectly satisfy the law of conservation of matter.
Let's connect all this to everyday life. Have you heard of fuel cell vehicles? FCVs are amazing. They generate electrical energy directly from hydrogen and oxygen. And you know what the coolest part is? This reaction produces only water as a waste product. Breaking down water and recombining it yields incredibly clean energy, packing a massive punch without any of the pollution. I want to end on this provocative transfer challenge for you. The decomposition of water is written as 2H2O yields 2H2 plus O2. Based on the coefficients and subscripts we just learned about, exactly how many total atoms of oxygen are conserved from the reactant side to the product side? And how might mastering this simple chemical process power the green fuel cell vehicles of our future? Think about the math and think about the real-world impact. Thanks for being a focused learner with me today, and I'll see you in the next explainer.